Welcome to the Q&A session 39 from the playlist of IIT-JEE Main Physics Part 2. The topic is the motion of a charge in a magnetic field, and based on this topic I have selected one question for this session, which is written here on this board. So here the question is: a particle of mass m and charge q moves with a velocity v along the positive x-axis as shown in this figure. It enters a region of uniform magnetic field B directed along the negative z direction, extending from x is equal to A to x is equal to B. So this is this line, that is PQ is is the line which is depicting x is equal to A, and RS is the line which is depicting x is equal to B. So the minimum velocity required for the particle to enter the region x greater than b, that is, we have to find the minimum velocity for this particle having a charge q, so that it just enters the region x greater than b. Means we have to find the minimum velocity so that this charge particle just touches the line RS. So now here the direction of the magnetic field is along the negative z direction. So this is the positive z direction. So the magnetic fields in the magnetic field is directed along the negative z direction. It means that the magnetic field is directed into the plane of the paper. That is, since the magnetic field is directed into the plane of the paper, therefore I have denoted the direction of the magnetic field with this symbol. This symbol indicates that the direction of the magnetic field is into the plane of the paper. Now the velocity of the particle is along the positive x-axis. So we know that if a charge enters a uniform magnetic field in a direction perpendicular to the direction of the magnetic field, then it will experience a magnetic force, and under its influence it will follow a circular path, and the circular path, the radius of the circular path will be equal to mv divided by q into b, where v is the velocity of the charged particle, m is the mass of it, and q is the charge on that particle, and b is the intensity of the magnetic field. Now we have to find the minimum velocity which is required for the particle to enter the region x greater than b. Means what we have to do means basically this means that we have to find the velocity, the minimum velocity with which it is able to just touch this line RS, because RS is basically depicting x is equal to b. So the minimum velocity required for the particle to enter the region greater than x is equal to b means that we have to find the velocity such that this particle is able to touch this line RS, which is depicting x is equal to b. So here R is equal to mv divided by qb. Now when the particle when a charged particle enters a uniform magnetic field in a direction perpendicular to the direction of the magnetic field, then it follows a circular path under the influence of the magnetic force. And now here in this case, the radius of this circular path, that is r, it has to be equal to, this is the origin, so this will be equal to b minus a, that is this one. So it is entering at this point. So this is the region of the magnetic field, that is from x is equal to a to x is equal to b. And when charge particle enters at this point, so it will, under the influence of the magnetic force, it will follow this path, and for the minimum velocity for the particle to enter the region x equal to x is greater than b, then we have to find the velocity such that it just touches this line RS. And for that purpose, the radius of this and because the velocity is perpendicular to the direction of the magnetic field, therefore it will follow a circular path and the radius will be equal to b minus a. So if I put the value of r as b minus a here, so I will get the minimum velocity v by this equation. So from this equation, I can say that v will be equal to, I can say the minimum velocity will be equal to b minus a into qb divided by m. So the correct option here is A, b minus a into b divided by m. So thank you very much for joining this session. In the next session, I will be again coming up with a different topic from the same chapter, that is the magnetic effect of current. So till then, have a nice day. Bye.